Dear friends, Maths Aspirants organizes a series of problem-solving sessions to help the students who are preparing for the forthcoming CSER NET examination. As a part of that series, today we have a session on linear algebra. Dr. Rahul Kumar, a postdoc fellow, IIT Kanpur, is with us to discuss some problems from the area of linear algebra. Dr. Rahul Kumar did his MSc from Cochin University of Science and Technology and did his PhD from IIT Madras. His broad research area is fundamental algebras. I would like to thank Dr. Rahul for accepting our invitation and joining with us. I hope that today's session will be really beneficial to all the participants. Welcome everyone to this program. Welcome, Rahul.
I'm thanking Vinod sir for making me part of this group. Also allowing me to present some problems from linear algebra in this session. I'm also thanking Biju sir for giving the technical support. Okay. Good evening to all of you. So we will be solving some few problems from linear algebra, just touching some concepts of from the scratch to what I mean is from the very scratch of linear algebra to some advanced topics. Yeah. Okay, sir. Okay, the first question is the following. Let A be a 2 by 2 matrix. Okay, 2 by 2 real matrix. Which of the following are true? The option 1 is image of A, so image under A of any straight line is a straight line. B, image of any straight line passing through origin is again a straight line passing through origin. C, image under A of any two parallel lines are parallel lines. D, or perpendicular lines. Okay, I hope the screen is whatever I wrote is clear to all of you. So I will read once again. Let A be a 2 by 2 real matrix. Then which of the following are true? First one is A of any straight line is a straight line. Option B, image of any straight line passing through origin is again a straight line passing through origin. C is image under A of any two parallel lines are again parallel lines. Then the final question is what about perpendicular lines? Means image of perpendicular lines will be perpendicular lines or not. Okay. So how many of you know the answer for this? At least, okay, we'll take the first option, option A. How many of you know the answer for A? Anybody knows? Or what is that? Like, I'm not asking the exact answer, yes or no. Hello? Anyone like make it as a discussion. Like I think that will be better. So what you suggest, sir? You know, sir. Hello?
Hello, sir.
Yeah, so okay. Now so we will see the answer for the option A. So what we are looking is image of a straight line under A. So what is the equation of a straight line? So equation of a straight line is nothing but ax plus by equal to z, right? This is the equation of a straight line. So it will be like a straight line with the x-intercept will be c by a and y-intercept will be c by b. So this is the origin. So what we are looking at is the image of this straight line under A. So that means we are looking at the set A of xy, right, such that ax plus by equal to c. So we want this set, the image of A under the so image of the points xy under A. That means those points are satisfying ax plus by equal to c, right? So how do we proceed with this? So okay, now we have this equation ax plus by equal to c. Can I write it like this? I can write it as a matrix, right? AB times xy equal to just c. The same equation I am rewriting in terms of matrix AB and matrix xy, the row matrix and a column matrix. Okay. So and now we want the image of A. So we want A of xy, right? Having the above property. So what I will do is I will plug the same equation. I will rewrite like this. It goes. Oh, okay. Did I mention that A is a invertible matrix? Sorry. Here a real invertible matrix. Sorry for that. Yeah. Sorry for that. Like A has to be an invertible matrix that I missed. So because A is invertible, I can plug A inverse A inside it, right? Yeah. Now A inverse, since A inverse exists, I can take this A inverse as some alpha 1, alpha 1, 2, alpha 2, 1, alpha 2, 2, right? Then what will be the matrix AB times A inverse? This will be nothing but A alpha 1, 1 plus B alpha 2, 1, comma A alpha 1, 2 plus B alpha 2, 2. So I'm calling these two vectors as some A dash and B dash, right? So the equation 1 I can replace as A prime B prime times A xy, that is equal to C. So what that means? So this is again a straight line, right? This is exactly the image of A of exactly the image of xy satisfying the property equation. What should I say? Equation 2 is exactly the image of equation 2 under A. So this is clearly a straight line, right? With the coefficients A prime, B prime, and the equality is equal to again C. So it is clearly a straight line. Is it clear to all of you?
Yes, sir.
So the first option is correct, right? The image of A, the image under A of any straight line is a straight line again. So now let's look at the second option. Image of any straight line passing through the origin is again a straight line passing through the origin. How to answer that? This is clearly a special case of the first, right? Any straight line passing through the origin means it is of the form ax plus by
equal to 0.
Yeah. So the image of the line, yeah, right. So this is a special case of the first. So so here under the image, the C remained as the same. Only A and B changes, right? A changed to A prime, B changed to B prime under the image. Under the image of the image of x, the line x comma y having the property ax plus by equal to C is nothing but A prime plus A prime x plus B prime y equal to C, right? This is the image. This is the image. So if C is 0, it's again going to be 0. The image is, for image also, the C is going to be 0. So it is again a straight line passing through origin. Clear, right?
Yes, sir.
Is it clear?
Yes.
Yeah. So the second option is also true. So now look at what is image of A, image under A of any two parallel lines are again parallel lines or not. How to answer that? Okay, I'm erasing this portion. See. So we have to look at the image of parallel lines. So what are the equation of the two parallel lines? So ax plus, okay, a1 x1 plus b1 y equal to c, and a2 x plus b2 y equal to c. This equation of parallel lines are just the a1 and a1 and b1 will change. The c will remain as the same. So under A, what will be the image? Under A, the first line, first one will be A1 prime x plus B1 prime y equal to C. 2 will be transferred as some A2 prime x plus B2 prime y equal to C. So these are again clearly 3 and 4. 3 and 4 are also parallel because for both of them the C is same. The coefficients are same. Coefficients of x and y are same, and the C remains the same, and the coefficients only changes. So the image is again a parallel. Image is again parallel lines. It's clear.
Yes,
Sir,
sir.
C being same, how does it imply they are parallel?
Sorry.
Uh, Just C, the constant term being same, does
Yeah.
not imply parallel, right?
Okay.
You have to check that.
Yeah. These two are parallel means
Actually,
the
the coefficient will
A1x.
be 7, C will be C1 and C2 actually.
Yeah. Okay. Sorry. Yeah. Right. Yeah. So this is C1. This is C2. Yeah. Okay. Sorry. Yeah. Okay. So again, if A1x plus B1y equal to C1 and A1x plus B1y equal to C2, basically the line will be like this. This is C by A, C1 by A. This is C1 by B1. The parallel line will be something like this. The C will be changing to C2 by A1. The y-intercept will be like C2 by B1. So these are the parallel lines. So the image will be again the C1 and C2 is going to be fixed for the image also. So they are also parallel lines. That is clear, right? Do I need to
Yes.
explain that more? So
No.
image is again images are again parallel lines. It's clear, right? Hello?
Yes, sir.
Yeah, okay. So what about perpendicular lines? If you take two perpendicular lines, whether the image will be again perpendicular lines or not. I'm leaving it as an exercise. Like a moment of thought will give you an answer that this is not going to be the case. Just consider some matrix, some invertible matrix, which takes x-axis and y-axis. So you consider the perpendicular lines as x-axis and y-axis, and which the image will images are not perpendicular at all. Think of an counter example for this. So I'm leaving it as an exercise. Okay. So we are done with the first problem. right? Yeah. So we'll move to the next problem. Problem 2. Okay. Let F be a field and N be a positive integer. Vector space of n by n matrices over F, which of the following matrices A in M of F are subspaces of M of F. Which means all A such that A square equal to A. So I will read the question once again. Let F be a field and n be a positive integer, and V denotes the vector space of all n by n matrices over F. For the time being, you can consider F as C, the set of complex numbers. So what we are considering is now Mn of C. Okay. So Mn of V is nothing but Mn of C. Fixing F is equal to C. For simplicity, just assume F is equal to C. Then which of the following matrices A in Mn of C are subspaces of Mn of C? The first option is all invertible matrices in Mn of C. Whether that will form a subspace. So to check
No.
something is a subspace, what are the okay, yeah, that's not going to form a subspace. So to check something is a subspace, what we need to know? X element of V and Y element of V, then X plus Y should be element of V, right? And that is the first property. And if X element of V and alpha element of C, then alpha X should be again element of V. If we have these two properties for the set, then we say that set is a subspace of the original vector space, right? Yeah. So here the first option is considering all invertible matrices. So this is not going to be a subspace, right? Clearly. How?
Because null matrices does not belongs to that set.
Sorry. Sorry.
Vector doesn't belong to the set.
Yeah, you can consider X as just 1, 1, 0, 0. Y as minus 1, minus 1, right? X is invertible and Y is invertible. But what is X plus Y? This is just zero matrix, right?
Zero matrix
So
does not belong.
yeah,
Yes,
so
null
X plus
matrix
Y.
does not belong to that set.
Yeah, so X plus Y is not invertible. X is invertible, Y is invertible, but X plus Y is not invertible. We needed that. X plus Y should be inside the subspace, inside that set itself. Then only we say it is a subspace. But here, that is not the case. So A is not a the first option is not a subspace. So what about the second option?
Not true.
Yeah, those are also not going to be a subspace. You can consider like x equal to some, what should I say? Yeah, 1 0 0 0 and y equal to 0 1. Okay, 0 0 0 1. X is not invertible clearly because 0 is an eigenvalue. Y is also not invertible. Again, y has a 0 as an eigenvalue. Then what is x plus y? It's nothing but identity matrix. But this is invertible, right? It's it's invertible and it itself is the inverse. Okay. So the second
Sir,
option
I
is
think
not true.
C option will be correct only.
Sorry.
Sir, I think C option will be correct only.
Yeah. C option only will be correct. That's what she's saying. Okay. Uh, let's see whether C is correct or not. So now the C option is saying you are collecting all A such that AB equal to BA for a fixed B. AB equal to BA for a fixed B. That means B is fixed. And collecting all A such that AB equal to BA. So clearly you can check that if A comma B element of, so okay, I'm calling that set as S. The set we are considering as S. Then we can see that A plus B. Oh, sorry, we already used A1 and A2 element of S. So A1 plus A2 is again S. How do we show? We need to show A1 plus A2 should also commute with B, right? That is something but A1B plus A2B. Now A1 commutes with B, so I can write as it is BA1. A2 also commutes with B, so I can write it as BA2. So that is nothing but B times A1 plus A2. So A1 plus A2 also commutes with B. Similarly, you can see that alpha times A1 is also element of S. So C is clearly a subspace, right? Yeah. What about the last option? Last option says
Not
A
true.
square equal to A. Sorry, the D option will be a subspace. What is the guess?
Not success.
No, sir.
Yeah, it's not going to be a subspace. So what you need to show? You consider some A and B, which are A square equal to A and B square equal to B. To produce some A plus B square. A plus B square is what? It will be A square plus B square plus AB plus BA. So A square is in A and B square is B plus AB plus BA. So we know, so what we need to cook up is find some matrix. Such that A, B plus BA not equal to 0. If that is the case, it will be A plus B the whole square will be A plus B plus something. It cannot be A plus B again. Then it cannot be in the subspace. So finding some examples like this will be easy. You just cook up some matrix having this property. Then we can roll out the D option as well. I hope this question is clear to all of you. Shall we move to the third option?
Yes, sir.
Yeah. That problem is okay. Which of the following are true. Option A, D from M and C to C defined by D of A equal to determinant of A is a linear transformation. B, only eigenvalues of the linear transformation T from M and C to M and C defined by T of A equal to A transpose are 1 and -1. Yeah, it has only two options. So which of the following are true? The first one is D is a linear transformation. Like they're claiming D is a linear map which sends a Mn of C to C defined by the D of a matrix is nothing but the determinant of that matrix. Then whether D is a linear transformation or not. So the next one is the only eigenvalues of the linear transformation T from MNC to MNC defined by T of A equal to A transpose are 1 and -1. So I think the question is clear to all of you. So let's consider option A. So what do you think? Option A is correct or not?
Not true.
Not true. Okay, before going to the answer, let me tell you what is a linear transformation. A map P from a vector space V to W is said to be a linear transformation if T of x plus y equal to T of x plus T of y, T of alpha x equal to alpha times T of x, where alpha is from the field F. So if a map having these two properties are called linear transformations. This I hope all of you know this. So now our question is, the map is defined as D from MLC to C, defined by D of A equal to determinant of A. So here the D will take MNC. MNC is a vector space of dimension n square over C, and the range will be C over C. It's a one-dimensional vector space. So the map is D of A equal to determinant of A. So claim the answer is D is not a linear transformation. How do we show this?
Sir, if you take A as identity and B as minus I.
Yeah, okay. It's D of A equal to 1, 0, 0, 1 and B equal to -1, 0, 0, -1. Determinant of A is what? Determinant of B is 1, right? Determinant D of A is 1. D of B is again 1. But what about D of A plus B? It is 0. So D of A plus B, yeah. So D of A plus B is not equal to D of A plus D of B. The first property is failing, right? So D is not a linear transformation.
Linear transformation.
Yeah. Okay. Before going to solve the second one, then just consider the map TR from M and C to C defined by TR of A equal to trace of A. Whether this will be linear transformation?
Yes, sir.
Yes.
Yeah. So this is a linear transformation, but determinants is not a linear transformation. Okay. So this is easy to check. So I just mentioned this. Now we will go to the option B. So option B is the only eigenvalues of the linear transformation T from MNC to MNC. It's a linear transformation from MNC to MNC. How it is defined? T of A equal to A transpose. So image is again a matrix. Image of A is A transpose. So this is a linear transformation. You can check. Check PT is a linear transformation. So they are claiming the eigenvalues of this linear transformation are only 1 and -1. So what do you mean by eigenvalue of a transformation T? A lambda element of C
Sir.
is said to be eigenvalue. That means T of X should be equal to lambda X, right? For some X not equal to 0. Then we say lambda is an eigenvalue and the corresponding eigenvector is nothing but X, right? So this is the definition of eigenvalue. I hope all of you know this. So now we look at this problem. So our T is nothing but defined as T of A equal to A transpose. Suppose lambda is an eigenvalue. Is an eigenvalue of T. Then what will happen? A X equal to lambda X, right? That is nothing but Ax is nothing but, oh sorry, Tx equal to lambda times X. Here X is I am taken as A. T of A equal to lambda times A, right? Then you say lambda is an eigenvalue of T, right? So what is T of A? This is nothing but A transpose. That means lambda A should be equal to A transpose, right? That means what? Suppose A is this matrix Aij. If A is the Aij matrix, then lambda times Aij equal to Aji, right? Right? Also lambda times
Yes, sir.
Aji will be what? Aij, right? Is it fine? Just equating the terms. Lambda times Aij will be Aji. Lambda times Aji will be nothing but Aij, right?
Yes, sir.
Yeah. So we have two equations, 1 and 2. So substitute that. So from 2 implies Aji equal to 1 by lambda Aij. Okay. Then 1 implies lambda Aij equal to 1 by lambda Aij. That means lambda square Aij equal to Aij. That means lambda square minus 1 times Aij equal to 0. Right? So I can choose this Aij to be a non-zero because A is a non-zero thing. A is not equal to 0. There exists some Aij not equal to 0. Right? I can choose that. So this product is 0 means then that should imply lambda square minus 1 equal to 0. That means lambda equal to plus or minus 1. Right? So the only eigenvalues of this transformation T from MNC to MNC defined by T of A equal to A transpose are just 1 and -1. Is this clear to all of you?
Sir,
Yes.
Yes, sir.
I have
Yeah,
doubts,
okay.
sir. Sir, lambda Aj is equal to Aji. Then second equation, how do you write this?
Yes, I am just equating the AJ times and AJ times. Consider the lambda A, the matrix, and
Sir.
consider A transpose matrix.
Okay, sir.
So AJ, the term AJ term as well as AJI terms. The
Okay,
corresponding terms you equate.
okay, sir. Okay.
Yeah. So those two will give you the first term 1 and 2. So the remaining all are just calculations. So from that, what we can conclude is lambda is just 1 or minus 1. Shall we move to the next question?
Sir, I have one doubt. Sir, if 1 and minus 1 are only eigenvalues, then for the eigenvectors, we will only have symmetric and skew symmetric matrices.
Means I didn't get this question. This transformation T is a T is from MNC to MNC. Okay.
Yes, sir.
Yeah. So are you looking at the matrix of this T?
No, sir. I am saying that our to find out lambda, we are taking A transpose equal to lambda A. Now,
Yeah.
only possibilities of our lambda is 1 and minus 1. So
Right.
if I try to find the eigenvectors, then
Yeah.
eigenvectors only are symmetric and skew symmetric matrices.
Exactly. Yeah. Right. For the lambda equal to 1 correspond to A equal to A transpose. That means symmetric matrix. Lambda equal to minus 1 means A transpose equal to minus A.
Yes,
And
sir.
yeah, skew symmetric matrix. Yeah, you're correct. Yeah. Okay. Shall we move to the next question? Hello?
Yes, sir.
Yeah. Okay.
Yes.
Yes, sir.
Okay. You said yes, right? Yeah. Fourth one. Let A be a 3 by 3 matrix with real entries such that determinant of A equal to 6 and trace of A equal to 0. If determinant of A plus I equal to 0, then eigenvalues of A are option A -1 to 3, option B -1 to -3, option C 1 to -3, option D -1, -2, and 3. Yeah. Okay. The question is, let A be a 3 by 3 matrix with real entries such that determinant of A is 6 and trace of A equal to 0. Then, an addition they are given that if determinant of A plus I equal to 0, then the eigenvalues of A are the which is the set of eigenvalue of A.
Option D.
Option D. Yeah. How do we claim this? Option D.
Sum of these eigenvalues are 0 and multiplication are 6.
Yeah.
And if determinant of A plus I is 0, then one of the eigenvalue must be 0. So eigenvalues of
one of the eigenvalues should be
0. A plus
Why?
I.
Yeah.
-1.
Yeah, one of the this condition, determinant of a plus I equal to 0 will imply that one of the eigenvalue is -1, right? So either A or B or D. This is not going to be the case. That is clear. So now, the determinant of A is given. Determinant of A is 6. So we know that if lambda1, lambda2, lambda3 are the eigenvalues, then determinant of A is nothing but lambda1, lambda2, lambda3. The product of lambda1, lambda2, lambda3 will be the determinant. And trace of A will be nothing but lambda1 plus lambda2 plus lambda3. This fact we already know. Now we already got that -1 is a eigenvalue, right? So I'm taking that as lambda1. Then what will be this lambda2, lambda3 into -1 will be 6, right? Because it is given that determinant of A is 6. So -1 times lambda2, lambda3 is 6. Also -1 plus lambda2 plus lambda3 equal to 0 because trace is 0. Since determinant of A is 6, this is means trace of A is 0. That means what? Lambda2 plus lambda3 equal to 1. Also lambda2, lambda3, the product is -6, which will imply that lambda2 equal to -2 and lambda3 equal to 3. So our eigenvalues are -1, -2 and 3. -1, -2 and 3. So the D option is the correct. The remaining all these are wrong.
Sir, what is the determinant A plus I equal to 0? What is the importance of determinant A plus I equals to 0?
Sorry, what's the
importance of determinant? Sir, importance of determinant A plus I equals to 0. Why?
Yeah.
What is the importance here?
Yeah, if determinant of A plus I is 0 means we will get that -1 is an eigenvalue, right? How do we find the? How do we calculate the eigenvalue? We calculate determinant of A minus lambda I, right? And we are equating that to be 0. And given that already given that A plus lambda I is 0, determinant of A minus times minus I is 0. This is given, right? So lambda equal to -1 is already a eigenvalue. That is clear, right?
Yes, sir. But
So
here from a determinant equals to lambda1 into lambda2 into lambda3 and trace equals to sum of lambda. From here to we already calculate the answer. No?
yeah, but it is like it won't be easy to calculate just with these two information, right? Just if you given just product and sum, is it easy to calculate the what are lambda1, lambda2, lambda3? There may be another possibility as well for this solution, but it's already given that this is 0. That means one of the eigenvalue is -1. Then that eases the calculation of finding the remaining eigenvalues. Okay.
Okay, sir.
Okay. Thank you. We will move to the next question. Question 5. let S equal to the set AB minus BA, such that A comma B element of M and C. This prime is equal to set of all A element of M and C, such that trace of A equal to 0. Then option A, span of S equals M and C. Span of S is a proper subspace of M and C. And C S prime is a proper subspace of M and C. Dimension of S prime equal to n square minus 1. So the question is, they have given two sets, S and S prime. S is defined as set of all AB minus BA, where A and B are varying over M and C. And S prime is nothing but the set of all A element of M and C such that the trace of that matrix is 0. Then the question is, which of the following are true? The first option is the span of S equals M and C. S is a subset, so this we can take the span of S. So whether the span of S will be full of M and C or not. Second option is span of S is a proper subspace of M and C. It may not be the full, so it can be a proper subspace or not. Then the third option, S prime is a proper subspace or not. Option D is dimension of S prime is n square minus 1 or not. So
Option D is a
Yeah,
correct option.
it's true.
which one?
Option D. Option D.
Option D. How do we calculate that? Like
Sir,
Actually, total dimension is n square, and the trace is the sum of the diagonal element. So from there we can get one equation. So n square minus 1 will be the dimension actually.
okay. So yeah, that is one way. So because the dimension of S prime is n square minus 1, that will definitely a proper subspace, right?
Yes,
S
sir.
prime will be a proper subspace. So if this is true, of course this is also true. In fact, it should come in the reverse way. S prime is a proper subspace because there are a lot of matrices with non-zero trace. So it is a S prime is clearly a subspace, right? That also you can check. If you take two elements, A and B, which have trace 0, then the sum will also have trace 0. If a matrix A has trace 0, then alpha times A will also have trace 0. So it is a subspace. And also clearly the dimension of that subspace is n square minus 1. So that is proper. So C and D are correct. Okay, I will explain this once again because it was she who explained that. I will explain later. So what about S and option A and B?
B is
option A is
true. A is
false.
wrong.
Sorry?
A is false
A
and
is
B is true.
false.
Yeah, how A is false?
Because we are getting the same thing. That means if we find trace of AB minus B, actually trace of AB and trace of B is equal. So
Okay. So you're saying S
so
and S prime are
yeah,
same set.
yes, sir. That means AB minus B, if we take AB minus B is some D, then trace of D equals to 0 we are getting again. So by the option C, we can claim that option A is
So
wrong.
you're assuming this fact that S is equal to S prime, right?
Yes is a
Yes,
subset
sir.
of S prime.
Yeah.
Not
S is
properly.
a subset of. Okay. S is a subset of S prime. S prime has dimension n square minus 1. So S will also have dimension less than n square minus 1 or equal. So it should also be dimension of S is less than or equal to n square minus 1. So S is also a proper subspace, right? So
Yes, sir.
this is wrong. This is correct, right? Okay, how to see that dimension of S prime equal to n square minus 1? So just before we had defined a trace, a linear transformation from M and C to C, defined by trace of some matrix A equal to trace of A, right? So the kernel of this thing will be nothing but S prime, right? Right? So if you define a linear transformation from MLC to C, defined as trace of A equal to TR of A, that is the transformation I'm defining, or I just did not write T. T of A is nothing but trace of A. Then our S prime is nothing but the kernel of T, right?
Yes, sir.
Yeah. Now we need the dimension of S prime, right? So which theorem connects with the dimension of S, the dimension of the kernel of something?
Triangle.
Yeah, rank nullity theorem. So what rank nullity theorem says? Suppose T is a transformation from V to W, V is finite dimensional, then dimension of range of T plus dimension of kernel of dimension of the null space or kernel of T equal to nothing but the dimension of V. Suppose V is n dimensional, it is n, right? So what will be the dimension of range here for our particular T? Look at this particular T. Yeah, so dimension of range of T is nothing but 1. So what is the dimension of V here? N square, right? So our V is M and C. So the dimension of M and C is N square. So if you apply the rank nullity theorem, what do you get? Dimension of kernel of T, that is nothing but dimension of S prime, that is nothing but N square minus 1. Right? Dimension of S square is N square minus 1. Right? Is it clear to all of you?
Yes, sir. How is the dimension of S is less than equals to n square minus 1? Sir, how do you discard the option E?
How do we discard option A? Yeah.
Yes, sir.
So okay, can we say that S is a subspace of S prime? S is a subspace of S prime, right? You take some element.
But buffer is given AB minus BA equals to 0. So
Yeah.
how can we say that?
Oh, okay. Someone. Okay, sorry. Okay, we will look at. So dimension of S prime is N square minus 1. That is clear, right?
Yes, sir.
Yeah. So this is N square minus 1. That is correct. Dimension of S prime. So S prime is a proper subspace of MNC. That is also correct. So we need to know about these two, A and B, right?
Yes, sir.
Yeah. Okay. We will see that. Option A. Yeah. So AB minus. So what is S? S is nothing but the set of all AB minus BA is that A comma B element of M and C. Now you are spanning this S, right? Suppose span of S equal to full MLC. Okay. Then what will happen? I can write identity as element alpha 1 S1 plus alpha 2 S2 plus etc. alpha n Sn, where S1 S2 etc. Sn element of S, right? This is possible, right? If that is true, if span of S is full MNC, I can write identity as the span of S, some elements from S1, some elements from S, right? Is it clear?
Yes, sir.
Yeah. Now we apply trace on both sides. Trace of identity equal to trace of alpha 1 S1 plus alpha 2 S2 plus etc. alpha n Sn. Now trace is linear, that we already noted before. Trace is a linear map, so I can just write it is nothing but the trace of summation of trace of alpha I Si, I equal to 1 to n, right? This is again I equal to 1 to n alpha I trace of Si, and Si's are coming from S, right? That means S is of the form AB minus BA, right? So what will be trace of Si? All will be 0, right? So the right hand side will be 0. But what is left hand side? This is nothing but trace of n. Identity is n. So n equal to 0. This is a contradiction, right? So that means what? I cannot write identity as a span of elements from S. That means what? S is not full MNC. S is a proper subspace actually. So S is a span of S is a proper subspace of MNC. This is wrong. Is it clear to all of you?
Yes,
Yes.
sir.
Yeah. Okay. Okay. In fact, just look at this problem once again. What we have taken is S. S is nothing but the set of all AB minus BA such that A comma B element of MNC. And we are taking the span of that set. And next is S prime. S prime is nothing but the set of all A element of MNC such that trace of A equal to 0. This is a well-known fact from 90s, 30s maybe. It is that S is actually S prime. You don't need to even take the span of S. S is exactly equal to S prime. If you are curious about this, I'm just like you can Google it, or you can look at this paper on trace 0 matrices by Professor V.S. the IMC 2002. So, in fact, this S is actually equal to S prime. That means what? Whenever you have a matrix for which trace of A equal to 0, that means A equal to some A1 B1 minus B1 A1. Reversely, if you taken some A1 B1 minus B1 A1, then trace of that will be 0. So this is the easy thing, but this is not at all obvious thing. That means if you take a trace of A is 0, that A can be written as A1 B1 minus B1 A1 for some matrix A1 and B1 in MNC. So if you are interested, you can just look at this paper, whatever I mentioned here, on trace 0 matrices by V.S. Sundar, Professor V.S. Sundar, IMC 2002. In fact, this is a well-known fact from 1930s. So please have a look at this if you are interested. Is it clear whatever I mentioned last? Hello?
Yes, sir.
Yes, sir.
Yeah. Sorry? Hello? Hello?
Yes, sir.
Yes, sir.
Okay. Okay. So we will move to the next question. Define t from C01 to C01 defined by t of f acting at x is nothing but integral 0 to x f of t dt. Then create t is 1 and onto. Option B, t is not 1 but onto. Option C, t is 1 but not onto. Option D, t is not 1 not onto. Okay. Defining a transformation from C01, that means set of all continuous functions on 0, 1 to again set of all continuous function on 0, 1. It is defined as t of f. T of f is a continuous function. Then t of f is again a continuous function. The value of that continuous function at the point x is defined as integral 0 to x ft dt. So this transformation is clear, right? How it is defined?
Yes, sir. Every continuous functions are integrable.
Yeah, right. Continuous functions are integrable, so you can integrate this. This makes sense. So the image of f under the point at the point x is nothing but integral 0 to x ft dt. So it is easy to verify that this is a linear transformation. The question they are asking is whether t is 1 and onto, t is not 1 but onto, t is 1 but not onto, t is 1 sorry, t is not 1 and not onto. So what is the guess? Anybody knows this answer?
T is not 1 and not off.
T is not 1 as well as not onto. The last option. Hello.
Yes, sir. Yes, sir.
Okay, let's look at this problem. So when we say t of t is 1, if and only if kernel of t is equal to kernel of t is just set of all f. T of f equal to 0 should imply f equal to 0. Then you say t is 1, right?
Yes, sir.
Sorry. T of some f equal to 0 should imply f equal to 0, right? T is 1 means the kernel of that t is just the set 0. T of f equal to 0 should imply f equal to 0. That then you say that t is 1. This is what we need to check now. Okay, let's consider some t of f equal to 0. T of f equal to 0 means what? T of f at every x is 0, right? T of f at every x is 0 means that is nothing but integral 0 to x f of t dt equal to 0. What does this mean? Integral 0 to x f of t dt equal to 0.
Sir, if
So
we take any
now
two constant
it is
function, then the integral value will be 0. That means fx equal to 2 and fx equal to suppose 3. Their image will be 0. But 2 is not equal to 3, so it can be said that it is not 1.
no, it is going to be 1.
Oh.
Yeah. So that's what I'm claiming. So now T of f acting at x is integral 0 to x ft dt equal to 0. Now what is fundamental theorem of calculus? FTC, fundamental theorem of calculus. Suppose you have a integrable function on set AB. So suppose we are looking for some function whose derivative is f. Then what is that f? Right? That f is given by, it is nothing but 0 to x ft dt. Right? This is what fundamental theorem says, right? You start with a continuous function f of f on AB. Okay, AB. Then we are looking for antiderivative of f. Antiderivative means you look for some function capital F for which the derivative is nothing but our small f. Then what is that f? That f is nothing but given by integrals a to x ft dt. This is the fundamental theorem of calculus. I hope all of you remember this. So what here it says, integral t of f acting at the point x is 0. That means integral 0 to x f of t dt is 0. That means what? Our capital F is 0. Right? Capital X, f of that x at every point is 0. So if f is 0, f dash is also 0. What is f dash? F dash is nothing but small f. That means what? F is 0. So if you assume that t of f equal to 0, we can conclude that f is 0. Right? That means what? T is 1, 1. So t is 1, 1. So this is correct. 1, 1 is correct. Sorry, not 1, 1. T is 1, 1. Is this clear to all of you?
Yes.
Should I explain once again?
Yes, sir.
Yeah, okay. Once again, I will explain. So we need to look the kernel of T. That means what are the f which maps under the image of T? What are the f which takes the value 0? So that's for that we are assuming T of f equal to 0. T of f equal to 0 means T of f is a continuous function. F is a continuous function, so T of f is also a continuous function. So that continuous function is 0 means what? T of f at every x is 0, right? So T of f at every x is defined by integral 0 to x ft dt. This is 0. This is what we have so far. Now applying the fundamental theorem of calculus. Fundamental theorem of calculus says if you start with a continuous function f on AB and we are looking for some capital F whose derivative is small f, then that capital F is given by f is equal to integral a to x ft dt. This is what fundamental theorem of calculus says. So if you apply fundamental theorem of calculus on this equation, what we get? That function capital F of x is 0, right? Because integral 0 to x f of t dt equal to 0 for all x. That means capital F of x is 0. That means the derivative of that is also 0. So what is the derivative of capital F? That is nothing but our small f. So small f is 0. What we started with T of f is equal to 0, but we could conclude through fundamental theorem of calculus that f is equal to 0. That means what? The kernel of T is just singleton set 0. That means T is 1, 1. Is it clear?
Yes.
I hope it is clear to all of you. Now look at onto, whether it is onto or not, whether T is onto. Okay.
Not onto.
Not onto. How you came that it is not onto?
We are getting differentiable function, but take a continuous function which is not differentiable.
Yeah, just T
Then
is
it is
defined
not-
like this, right? So what will be the T of f acting at the point 0? Let f be any function. F be any element of z0, 1. Then what will be the image of T of f at the point 0?
0.
It will be integral 0 to 0 f of t dt, right? This is nothing but 0. So what it says, if you take any continuous function and if you consider the image of that and consider the value of that image, consider the value of that image at the point 0, it will be 0 again, right? That means T of f at 0 is 0 for all f element of C01, right? So whatever be the image you consider, the if you evaluate the value of that T of f at 0 is 0, but our range is what? Range is C0 function, right? Any continuous function you can take, but the image will contain only functions whose value at 0 is 0, but there are continuous functions which takes non-zero values at 0 as well, right? So T is not onto. So the answer is T is 1, 1, but not onto. Is it clear to all of you?
Yes, sir.
Please ask if it is not clear to you. T is 1, 1, but not onto.
Once again, repeat not onto, sir.
Okay. Onto means what? Every continuous function should have a pre-image, right? Right?
Yes, sir.
No?
Yes, sir.
Yes, sir.
Yeah. Now we are looking at the image T of f. You start with the function f, and T of f acting at the point 0. What is that? It goes 0 to 0 ft dt. That is equal to 0. That means what? T of f, the value of T of f. Value of T of f at 0, at the point 0 is 0, right? For all f. Is it clear?
Yes, sir.
But there exists continuous function for which there exists continuous function g for which g of 0 not equal to 0, right? So if you take a continuous function for which continuous function g for which g of 0 is some 100, if you start, you cannot get a pre-image for that. Why? For any f, the image T of f will take the value 0 at the point 0, right? So this continuous function g, whatever we started with, will not have a pre-image. That means T is not onto. It's clear now?
Yes, sir. Yes, sir.
Okay, thanks.
Sir,
Okay.
sir, here we are defining a transformation from a vector space to another vector space that have same dimensions, right? So
Yeah, right.
Can't it be
Yeah, okay.
isomorph? So it
Yeah.
can be one and onto.
Yeah.
Can you explain it?
Yeah, wait. Okay, what is the dimension of this space? It is infinite dimensional, right? C01
Yes, sir.
contains all the polynomials, 1, x, x square, x cube, all are linearly independent. You can verify that. That means what? For any n, you can find a set containing that many linearly independent vectors. That means this set is infinite dimensional. C01 is infinite dimensional, right?
Okay, sir.
So if C01 is infinite dimensional, it may not be okay. So this C01 is infinite dimensional, and what we got is the transformation T is 1, 1, but not onto. Now the next problem we'll consider what happens if you work with finite dimensional vector space. Okay.
Okay, sir.
Okay. I'm moving to the next problem. We are moving to the 7th problem. Okay. Let T from V to V, and V is finite dimensional. Then A, T is 1, 1, not onto. B. T is not 1 1 but 1 on 2. C. T is 1 1 and on 2. Okay, I need to modify this question. Okay, let me put it in this way. Is finite dimensional, then T is 1 1 if and only if it is on 2. Is it true? Is it true? Like T is a linear transformation from V to V, which is a finite dimensional vector space. Then T is 1 1 if and only if it is on 2. And is it true or not? This is the question.
Sir, it is true.
Yeah, this is true. What is how we know that this is true?
Rationality.
Yeah, exactly. So I'm not going to the details of this. Rank nullity. It's actually a easy theorem, like easy statement from rank nullity theorem. Says it is true, right? So I'm because there is not much time for to proceed. So I'm not going to the details of this. Just look at rank nullity theorem. It says that if this is a finite dimensional space, it is 1 1 if and only if it is on 2, right? But we in the next just before problem, the sixth problem, what we saw is if the vector space is infinite dimensional, there can be possibility that it is 1 1 but not on 2, right? Yeah, but when the vector space is finite dimensional, it is 1 1 will imply it is on 2 will imply it is 1 2. This is if and only if. Move to the next problem. Let A be an n by n matrix which of the following okay, this is a question. Let A be an n by n matrix which of the following are true. Okay, and f of t is defined as a function. Function is defined as f of t equal to -1 whole to the power n, t to the power n plus a n minus 1, t to the power n minus 1 plus etc. a naught, where a1, a2, etc. all are real numbers. Then the dimension of the span of identity and a square, a cube, a to the power 5, 6, all nth power of a you take, then you span that space. The dimension of that is always less than or equal to n. The B option is if f of t, whatever the f of t we defined, is a characteristic polynomial of a, then a is invertible if and only if a naught not equal to 0. Third option is if a is invertible, then that a inverse can be written in terms of above polynomial. So how do we proceed with this? Okay. So you have given a matrix A, which is of the diamond n by n matrix. Now you consider the span of identity a square, a cube, etc. Then the dimension of that space is less than or equal to n. What is the answer for this? Anybody knows?
Answer C.
Sir,
A, B, C.
Sorry?
B is true, right?
A is true.
A is true. Okay, how we okay, let's look at one by one.
Also true.
Okay, we can see one by one. Let's look at what is A. Consider the space F is equal to the span identity A a square, a cube, etc.
Monday जा रहे.
Sorry.
If A is not invertible, then option A is false.
Option A is false.
So,
How?
if A is not invertible, then A
Like
dimension
A is
of
not given to be invertible or not invertible. A is a matrix. That's all we know. Okay, let's look at this. So F is the span of this space, identity, and a square, a cube, etc. So here this is a application of Cayley-Hamilton theorem. What Cayley-Hamilton theorem says?
Sir, the matrix will satisfy the characteristic equation.
Yeah, the matrix A will satisfy its characteristic equation, right? So now can we guess? Is it now can you guess how to proceed with A?
Yes, any A power n plus 1, etc.
Yeah. Okay. Let's also, I don't have space now. Yeah. Claiming that in a square, etc. a to the power n minus 1. If you take this set, is a family of n vectors which spans F. If I show this, then the dimension of F will be less than or equal to n, right? Family of n vectors which spans F. Then if I prove this, then the dimension of the span of F will be less than n, right? Less than or equal to n. Okay. So by Cayley-Hamilton theorem, what we have is, now we can write a to the power n as some an minus 1, an minus 1 plus etc. a naught identity, right? You can write the nth power in terms of its lower powers, right? By Cayley-Hamilton theorem. Is it clear? So what you have to do is find the characteristic equation. It will be a polynomial of nth degree. So it will be, suppose that polynomial is f of t equal to minus 1 whole to the power n tn plus etc. A1t plus a naught. Then what we have is Cayley-Hamilton theorem says this is true. Type. This is equal to 0. So from this equation, I can write an in terms of the remaining an minus 1, an minus 2, etc. Minus 1, an minus 2, etc. Identity. So an can be written as the span of this, right? Yeah. So if you want to prove from a to the power m for m greater than or equal to n, that can also be written in terms of this space element by induction. Try with induction on m. So any element a to the power m which is greater than or equal m is greater than or equal to n can be spanned by this kind of elements, right? What was our f? Our f was Yeah. Our F was spanning of this set, infinitely many elements, but that can be actually spanned by some n elements. So the dimension of this space is less than or equal to n. Is that clear?
Yes, sir.
Yeah. So this is true. First option is true. Okay. So what about the second option? What second option says?
It is true,
Uh,
sir. If it is a characteristic polynomial, then A0 denotes
Yeah, suppose f of
determinant.
yeah. So if f of t is this is the characteristic polynomial, then what will be the value of f of 0 equal a0, right? A0 is nothing but f of 0, right? This is nothing but determinant of a minus 0i, right? This is nothing but determinant of a. So from this, what we can conclude is determinant of a is not 0 if and only if a0 is not 0, right? That means what? Whenever determinant of A is non-zero, it is an invertible matrix. That is an if and only if condition. That means this implies A is invertible. If and only if A0 not equal to 0. Is that clear?
Yes, sir.
Yes, sir.
Yeah. So the second option is also true. What about the third? Third is clearly an application of Cayley-Hamilton theorem, right? If A0 is non-zero, you can divide by that, and you can write A inverse in terms of this. Just check it. It's
Sir,
again application.
how
Yeah,
you
sorry.
write f of 0 as determinant of a minus 0i?
Yeah, f is the characteristic polynomial, right?
Yes,
F is the
sir.
characteristic polynomial. So how characteristic polynomial is defined? It is defined as the determinant of, like how it is calculated, determinant of a minus 0i, right? F of lambda will
Okay,
be
sir.
determinant
Okay,
of,
sir. Yes, sir. Okay.
yeah. So 0 is nothing but 0. So it is nothing but determinant of a. So a0 is nothing but determinant of a. So determinant of, yeah, a is invertible if and only if determinant of a is not 0. That is if and only if a0 is not equal to 0. So that's how B is correct. So for C, I'm requesting you to check it. It's again an application of Cayley-Hamilton theorem. If A0 is not 0, determine it's invertible. So again, from the Cayley-Hamilton theorem, that equation, you can manipulate that. A inverse can be written in this form. Please check it. Okay, we will move to the next problem. Better we should stop here. Already 1.5 hours, right? It's like too much of math is also not good, I guess. Okay, so I'm
Yeah,
stopping
okay.
here.
Yeah, thank you.
Yeah.
Thank you, Rahul.
Yeah, thank you, sir.
Thank you, Dr. Rahul, for this nice session with a good collection of problems from linear algebra. Dear
Thank you, sir.
participants, now it is your time to share your feedback and ask your queries. Feel free to share the feedback. And if you have any queries regarding preparations for exams or IIT Madras or anything like that, you may ask now. Yes.
Yeah.
Yes.
My name is Sufra Kundu and I came from West Bengal. So sir, thank you. Very collection, your collection is very good. Problem. And
Okay, thank you.
I ask, please suggest any reference on linear algebra. That means any problem solving book. Please suggest.
I think Hoffman Kunsti is one of the good book, I guess. Otherwise, if you are looking for a problem-oriented book, you can look at Friedberg, Linear Algebra by Friedberg. It has a lot of like problems are explained in those books, in that
Sir,
particular
please
book.
repeat. Sir, please
Friedberg.
repeat.
Fried, F-R-I-E-D, Berg, B-E-R-G, Friedberg. I think the spelling is correct, I guess. You can just Google
sir,
it,
okay.
Friedberg, Linear Algebra, and get it for sure.
Okay, sir. Okay, thank you.
Yeah, sure.
Yeah, thank you.
Thank
you,
you,
Subra.
thank you, sir.
Yeah.
Yeah,
Thank you,
welcome. Thank
sir, for your dedication for me. Thank you, sir.
Yeah.
Okay.
Good.
Yeah, let me add one thing. There is a book called Handbook of Linear Algebra, written by a set of authors, which contains a lot of, almost all the topics as points, and important results are consolidated. I will try to share it in our group. It's a very huge one, but its PDF is available. Handbook of Linear Algebra. Okay. It will be
Okay,
really
sir, okay.
useful. I will share it in the our groups. Okay.
Okay, sir. Thank you, sir. Thank you.
Okay, others?
Sir, I have one doubt.
Good evening, sir. Yeah, okay.
Yeah, Sankhvi, could you
Hi,
introduce? Could you introduce
Sir.
yourself first?
I'm Sanghavi, did my MSc. Now I am preparing for competitive exams.
Okay. So you are from which place?
So I'm from Erode, Tamil Nadu.
Okay. Yeah.
Okay.
Sir, in last option, if A is nilpotent matrix, what about the dimension? Sir, if A is nilpotent.
Yeah, is nilpotent means for some power of m, some power of a to the power m is for some m, a to the power m is 0.
Yes, sir. Yes, sir.
Right? Yeah.
Okay.
That means what? So a to the power m is 0. A to the power, if a to the power m is 0, a to the power m plus 1, a to the power m plus 2, everything will be 0. Right? Yeah. Now again apply the Cayley-Hamilton theorem to see what is the dimension. Think about it.
Okay, sir. I will try.
Yeah, sure.
Thank you, sir.
Okay.
Yes, Dia.
Good evening, sir. Thank you, sir, for your wonderful session. The session was very nice, and I really liked how you explained those problems. Thank you, sir.
Welcome. You're welcome.
Thank you, Dia. Yes. Yeah, Dharmendra, you can speak now.
I am Dharmendra Singh from Visakhapatnam now. The session was very nice, and problem are very nice and useful for CSIR net and other exam also. Sir,
Sure.
Rahul sir, can you share your PhD and postdoctoral experience, and what is your broad area, and you said polynomial. Can you
Sorry, what did you say last?
experience your?
Yeah, okay.
Yeah.
So I completed my
asking me about polynomial algebras.
Yeah.
Your research area.
Yeah. I completed my PhD in last November from IIT Madras. So my area is fundamental algebras. Fundamental algebras means it's a part of operator algebras, you can say. So operator algebras means like the study in which you have a collection of operators and study the properties, the algebraic properties of those operators. So it is different from operator theory. Operator theory, what you study is the particular operator and the properties of that operator. So operator algebra means you have a collection of operators and you study the property, the algebraic as well as other properties of collection of operators. So there is something called fundamental algebra. That is a particular type of an operator algebra, which has a lot of application in quantum physics.
Okay, thank you, Dharmendra. Others?
Thank you, sir. Your problems are very helpful, especially the first problem, like those straight line problems is very interesting.
Sneha, could you introduce yourself?
I'm Sneha Shardar from West Bengal, and I'm pursuing my MSc from IIT Bhubaneswar.
Okay, great.
Thank you, Sneha. Yes, others?
Good evening, sir.
Yeah, yes, Shikha.
Good evening, sir.
I am Shikha and currently pursuing integrated MSc from Birla Institute of Technologies, Mishra, Jharkhand. Sir, your session was really nice. You explained each and every options that why it is correct and why it's not. And sir, I would like to ask few last minute tips for preparation for CSIR NET.
Last minute tips means what I can say. Basically, math is all about like doing maths. That's only way you can learn. So I think that's the main thing you have to follow. Like whether it is CSR exam or other exams. If you are interested in math, you should do math with paper and pen. Then you improve.
Okay.
Yeah,
Okay.
Siga, I may add one point in that. As it is very near to the exam, I think it will be better to go through in the reverse way. You can analyze the question papers, previous question papers, and recollect the necessary theory regarding that. You can brush up the theory needed in that problems. See, as it is in the last moment, it is not easy to cover all the things and go back to it.
So when is the exam, sir?
I think it is around June 7 or 8, something like that. Siga, could you get the...
So exact date is not released yet. It's 6th, 7th or 8th.
Yeah.
Okay. Yeah, that means you have only few more days. So better to refresh things. But you don't try to study new things. Whatever you learned already, you try to refresh.
Okay, sir.
Okay.
Thank you, sir. Thank you, Vinod, sir, for organizing such sessions. Thanks a lot.
Good evening, sir.
Yeah, yes.
Sir, I am Nandakumar from Tamil Nadu, sir. I have completed my postgraduate, sir. Thank you, sir. Your session was such wonderful. Since your explanation, as it is the basic level explanation, sir. Thank you so much, sir, for this wonderful session. And thank you, Vinod, sir, for conducting this wonderful session, sir. Sir, I have I need one suggestion from you, sir.
Yes.
How should one approach a linear algebra problem in generally?
Yeah. So you should. Okay. One thing I will ask you. So in plus twos, the plus two is the place where like you start encountering matrices, right? Yeah. So
yes, sir. Yes,
when
sir.
you add two matrices, you add term wise. When you subtract matrices, you subtract term wise. But when you multiply it, you complicate it.
Yes,
why one is doing in that, like why multiplication is not term wise? Why multiplication is very complicated way? You could have multiplied with like a times b is just term wise multiplication. Right? That was also possible, but why we didn't do that, right? Why we didn't do? Because the matrices are nothing but the realization of linear transformations. So
yes,
if you have a matrix, you have a transformation, linear transformation, whatever I explained in the session. So also corresponding to any linear transformation, you have a matrix as well.
Yes, sir.
So
yes.
if you start with two linear transformations T1 and T2, there are corresponding matrices A and B. So if you have two matrix transformation A, T1 and T2, the composition also you can make sense. So what will be the matrix corresponding to the composition? How that composition matrix is depending on A and B. So that is how like the multiplication is defined for this particular reason. So that the composition matrix should be the multiplication of A and B.
Yeah.
So
yes,
you have to define matrix in that way, the product of the matrix in that way. Only it makes sense. So you realize matrices as linear transformations, and then you proceed. That's how you start with linear algebra. I guess. Like that's what I feel.
Yes. Yes. Thank you.
Plus twos and all, like we will not realize this. We will like just multiply it as it is. The teacher will tell you this is how it should be multiplied. You are following it. But I think you should realize it as a transformation and understand. Also, the book, the Strang book is very good. You get a lot of intuition, like geometric intuition behind matrices.
Yeah. Yeah, Nandakumar.
Yes, sir.
Let me add one or two points regarding that. See, yeah, in linear algebra or any other advanced studies, we are doing the things in an abstract way. So matrix is somewhat, it is a way of representing linear transformation. So that is the way in which we are approaching problems. And one more thing to add is that, see, Rahul already told that, matrices are adding 10 ways, and scalar multiplication is also 10 ways. Why you are not multiplying matrix in that way? Yeah, of course, as it is being the realization of linear transformation, in order to get the product of matrices as the matrix of the corresponding composition of the corresponding linear transformation, we need to multiply in that particular way. Then only you will get like that. But there is actually another there is another sort of multiplication, like a term-wise multiplication is also there, which is known as Shor product or Hadamard product. And there are some theories regarding that. Of course, the properties with respect to that multiplication will be entirely different with this. There is some famous result called Shor product theorem like that. So you can search in Google to get more information regarding that.
Sure, sir.
And one more thing, Nandakumar, from next time onwards, try to speak with video. Feel free to do that. It will be a nice experience. Okay.
Sure, sir. Sure, sir. Since it's a night time, my video is not visible, sir.
Okay, no problem. I have just it's a common comment to all the participants. Feel free to share your views with a confidence mind. No need to shy or no need to feel any kind of hesitation to express your thoughts. Feel very free. Our platform is completely open, and really we are encouraging all the people to discuss maths. So feel free to do that. Okay.
Sure, sir. Sure, sir. Thank you. Thank you so much, sir. Thank you so much.
Yeah. Others?
Sir?
Yeah. Yes, Archana.
My name is
Archana. Yes.
Archana. I'm from Kerala. I completed my MSc. I'm preparing for my section, and today's session was very useful. And thank you, sir, for the.
Yes. Yes. Yeah. Another. Yes. Yes. Galaxy. Yeah. Yes.
Sir, I am Sri from Kerala. Sir, actually, I wanted to know about the interview of IIT Kanpur. How was your IIT Madras? How was your PhD interview there? Can you share, please?
It was almost 5-6 years back. I gave my interview for PhD. So PhD, like if you are good enough with your basic math, then you will pass the interview for sure. It won't be a hard thing.
Okay, so what kind of question they will ask?
It's up to whatever is your interest. If you're interested in linear algebra, they may ask some. You should choose, right? What is your area before you going for the interview? Which area you're going to do research? So it's accordingly the professors will ask questions to you. If it is abstract algebra, they will ask questions, basic abstract algebra things. If it is topology, or functional analysis, differential equations, all those. So whatever is the interest that you focus and prepare accordingly.
Okay, sir. Thank you.
Yes. In our group, we used to share the questions collected from the interviews prepared by those persons who are attended that. So just go through that, you will get an idea about the questions.
Yes, sir.
Yes. Others?
Hello, sir.
Yes, Sharda.
I'm Sadhana from Kerala. So thank you very much for the session. Thank you for your patience that you explained every point in detail. Thank you so much. And Vinod sir, thank you so much for organizing such a wonderful session. Thank you.
Thank you. Thank you.
Yes. Yes, Nasmia.
Hello, sir. I'm Nazmia from Sussex College, Kerala. So the class was very nice, even though it is an online session. The class was very interactive throughout. Thank you, sir, for the class, and thank you, Vinod
Thank you.
sir, for putting up the session.
Okay, Nasmia, thank you.
Thank you.
Yes. Others? If any of you would like to share any comment or like to ask any queries, you can do it now. Yes. Yes.
Hello, sir. I'm Kodai from Pondicherry. Sir, you
Yes.
explained about the interview. Before interview, was there any written test or how did you get through?
Yeah. Usually in IIT Madras, not only in IIT Madras, almost all IIT, there will be an exam, written exam. So those who qualify the written exam will go for the interview.
Okay, sir. And can you tell us about what is postdoc and what do you do there?
Yeah, postdoc is basically about improving your research capacity. Basically, in PhD time, you will just start realizing your area, whatever it is, whether it is operator theory or operator algebra or function analysis or differential equation. In PhD time, you will learn very less, even though like you have to find a new thing, right? So you just touch the subject. So to improve your research quality, you do postdoc with some another professor, so that your knowledge in that particular area will be broad, so that it will be useful for your further research. For that, you do postdoc. It makes sense to you?
Yeah, I think it will be, you will be more free to do research and you can go for more collaborations and all that.
Yeah, right.
Thank you, Kodai.
Okay, sir. Thank you. And today's session was very good. It was very helpful. Like it was recalling all the basic concepts. It was helpful.
Yeah. Thank you.
Okay. Yes. Any others?
Hi sir, I am Parvati from St. Teresa's College, Kerala. Today's session was very interesting. Thank you, Rahul sir, for organizing such a session. And a special thanks to Vinod.
Okay. Thank you, Parvati. Yes. Miss Lakshmi.
Hello sir, I am Lakshmi. I am from TMG College, Tirur, Kerala. Today's class was really interesting and informative, and you explained each and every question very clearly. And thank you sir for spending your valuable time with us, and thank you Vinod sir for conducting this class. Thank you.
Thank you.
Thank you, Lakshmi. Any others? Akita? Or, yeah, if any of you would like to express, yeah, yes.
Hello sir.
Akita.
I'm Agita from TMC College, Tirur. Today's class was very nice and interesting. Thank you, sir, for your valuable time with us, and thank you, Vinod, sir, for conducting the section. Thank you.
Akita. Is any others? If any of you would like to share the feedback, please do it now. We are almost to wind up. Arpita, are you there? Arpita Mandal?
Yes, sir.
Yeah, could you say something or introduce you? Please introduce yourself.
Sir, my name is Arpita and I am from West Bengal. Actually, I am doing my research in fluid dynamics, but I want to actually sit to coming to the NET examination. So that's why I'm just preparing for that. From NIT
Okay.
Jamshedpur, I
All
am
the best.
doing
All
it.
the best. All the best. Yeah. All the best.
Thank you, sir.
So where are you doing PhD?
Sir, NIT Jamshedpur.
NIT Jamshedpur. Okay. So
Thank you, sir.
I think you are in our WhatsApp group.
Maybe not, sir, actually.
Otherwise, please message me in my number. I will give it in the chat message. Okay.
Okay, sure, sir. Sure.
Okay. All the best for your research and further studies.
Thank you, sir.
Any others? Any of you would like to share any feedback? Please do it now. Let's make it quick. We are almost to wind up. See, many of students, not having the habit of speaking. I think especially from students from Kerala feel very less confident to speak things. Okay. Anyway, thank you, Rahul, for this nice session.
Yeah.
This is
Thank you so much for making me part of this. Actually, also all the best to all of the candidates who are going to attend this exam.
Yeah, this is the first time Rahul is engaging a session in our platform. I hope that you will do more sessions in our platform.
Yeah,
and your
in fact, this is the first time I am doing a online session.
Okay, what about your experience? I think
it was really nice. Like students were really responding good. It's clear they are really motivated and
and also we have a good, we have a good audience from different places of India.
That is somewhere from Bengal, somewhere from
yes, Arpit, do you want to say something?
Sir, if possible, please conduct one class equation and abstract algebra if possible.
Yeah, Arpita, we have already one session on abstract algebra in the beginning. Okay, you just message me in the number I have given. I will share that recording of that.
Okay,
so, differential equation we are trying to arrange possibly before the NET examination. We will arrange 3 more sessions from different areas. So, join our group. The information will be shared through that. Okay.
Thank you.
So, I expect Rahul will engage more sessions in our platform. Our group. Our group is actually being started in the year 2017, and we are now in the 6th year. And we had arranged more than 100 these type of problem solving sessions. So I hope that your expertise and teaching skills will be more beneficial for our participants, our members. So I expect your cooperation. And once again, I would like to thank you for today's session. Okay, thank you everyone.
Thank you so much, sir. Okay, thank you. Bye.
Bye.